Have you ever stopped to think about the tiny lights that power basically our entire modern world? I mean, they're in the screen you're looking at right now, they're lighting your home, they're everywhere. But how do they actually work? Well, let's dive into the amazing science behind the LED. So, to really get why LEDs were such a revolution, you have to ask a pretty fundamental question. For more than a century, the only way we knew how to make light was to get something really, really hot. But what if you could make light without the fire? What if you could skip the heat altogether? And that, right there, is the huge difference. An old-school incandescent bulb is basically just a controlled fire inside a glass bubble. You run electricity through a tiny metal wire until it glows white-hot. But an LED, it does something way more elegant. It convinces light to come directly out of electrons as they move through a special material. Okay, so how is this totally different kind of light actually made? Let's get into the basic principle that makes an LED tick. It's pretty amazing. The fancy scientific name for this whole process is electroluminescence. And what it means is actually pretty simple. It's a direct conversion. You put electrical energy in one end, and you get light energy, photons, out the other. There's no middle step, no heating element that wastes a ton of that energy. It's just straight from electricity to light. Now, to see how this works, we've got to shrink ourselves down and go inside that tiny semiconductor chip at the heart of every single LED. This is kind of like the engine room, where this really carefully choreographed dance happens between two very important partners. Okay, so the semiconductor is made of two special layers. First, you've got the N-type layer. It's been doped with stuff that gives it a whole bunch of extra free-roaming electrons. Then you have the P-type layer, which is doped to create holes, which are pretty much what they sound like, empty spots where an electron should be. You can think of it like a dance floor, right? One side is packed with negatively charged electrons, and the other side has all these open, positively charged spots just waiting to be filled. So when we apply a voltage, boom, the music starts. The electrons get pushed from their crowded side toward the middle, and the holes get pushed from their side to meet them. And right there in the middle, at the junction, an electron finds an empty spot and falls in. This is called recombination, and that drop from a high-energy state to a lower-energy one releases a little burst of energy. And that energy is a single particle of light, a photon. Now imagine billions of these little reunions happening every single second. That's the steady light we see from an LED. So what color is that light? Well, that is decided entirely by the materials you use to build the LED. The amount of energy that gets released when an electron falls into a hole, that's called the band gap, determines the color. Think of it like a waterfall. A really big drop releases a lot of energy, creating a high energy color like blue. A smaller drop, that releases less energy, creating a lower energy color like red. Seems simple enough, right? But this is where we hit a massive, massive roadblock. So here's the crucial thing. For decades, scientists could make red and green LEDs pretty easily. But one color, the most energetic and important one, turned out to be almost impossible to create. And without it, well, modern lighting just couldn't exist. And yep, that missing color was blue. I mean, think about it. To make clean, efficient white light, you need all three primary colors of light: red, green, and blue. For years and years, the blue LED was the absolute holy grail of solid-state physics. It was a puzzle that stumped some of the smartest people on the planet. The whole problem was with the material itself, gallium nitride. So to create that P-type layer, the one with all the holes, scientists used magnesium. But here's the catch. Pesky hydrogen atoms that were hanging around during the manufacturing process would literally grab onto the magnesium atoms and neutralize them. No active magnesium, no holes. No holes, no light. The breakthrough, which actually won a Nobel Prize for Shuji Nakamura, was to bake the material after it was grown. This heating process, called thermal annealing, literally boiled off the hydrogen, which finally woke up the magnesium so it could do its job. But get this, even after that massive breakthrough, the process was still insanely inefficient. Look at that number. For every single useful hole they managed to create in the material, they had to stuff in about 100 magnesium atoms. It was just an incredibly stubborn and difficult thing to pull off. And this chart just lays it all out so perfectly. For red and green LEDs, the whole process was easy. It happened naturally and was almost one-to-one efficient. For blue LEDs, you needed a difficult material, an entire extra baking step, and it was massively inefficient. Cracking this code, though, it absolutely changed the world. So once the blue LED was finally conquered, a new race began. How do we make these things way brighter? and way more efficient? The answer was to go quantum. The next giant leap forward was something called a quantum well. And what it is this unbelievably thin layer of semiconductor material. We're talking just a few atoms thick that's sandwiched between other materials. So what does this tiny little layer actually do? Well, you can think of it like an energy trap. Before, electrons and holes might just fly past each other in the junction without ever meeting. But this quantum well, it creates a kind of energy valley. When the electrons and holes fall into it, they get stuck there together, which dramatically increases the odds that they'll find each other, recombine, and create a photon of light. This was an absolute game changer. The efficiency went through the roof. But what's even cooler is that engineers figured out they could perfectly tune the color of the light just by changing how thick the well was. And then they started stacking multiple wells on top of each other. And that's how we got the super bright LEDs that we have today. And that brings us right to the cutting edge. This quantum technology has now evolved again into something called quantum dots. But what's really wild is how they're used completely depends on whether you're trying to build a TV or just a better light bulb. So a quantum well traps electrons in a flat sheet, right, in one dimension. Well, a quantum dot takes that to the next level and traps them in a tiny little sphere in all three dimensions. And that gives engineers even more precise surgical control over the exact color of light they produce. Now, what I find so fascinating about this is how it shows two totally different goals. In a QLED TV, you have a sheet of these quantum dots sitting in front of a pure blue backlight. Here, the goal is vividness. The dots soak up that blue light and then re-emit it as incredibly pure red and green, giving you this huge, vibrant range of colors. But in a high-end light bulb, the goal is quality. The dots are mixed right in with the LED itself to fill in the missing colors in the spectrum, making the white light feel much more natural and warm, almost like real sunlight. And that really leads to a pretty amazing final thought. We've gone all the way from a simple diode to manipulating quantum physics on an atomic scale. The next step isn't just about making light anymore. It's about making the right kind of light. So what if the lights in our homes could perfectly mimic the sun as it moves across the sky, changing their color and intensity, not just for how we see things, but for our actual health and our well-being? That's the incredible future this technology is now making possible.